And Hiroshi will now talk to us about optimal CHC solving via termination proofs. Again, the floor is yours.
Thank you. It's me again. And well, this is also about verification of open programs. Open programs, given an open program P that invokes an unknown external function F, techniques called maximal specification synthesis can synthesize a maximally weak specification of the external function F among those ensuring the safety of the open program P. Let's use this example program to illustrate our approach. So this program has a smooth root. It initializes the variables s and I to 0 and non-deterministically repeats the root and non-deterministically increment I by 1 or invokes the external function f with the actual argument I, and if it terminates and returns some value, accumulates s with that return value. And the program asserts that s is greater than or equals to 0. This is the specification we'd like to verify. And so the question here is, what is the specification of f that ensures the safety of the open program P? For example, if the external function f always diverges, then we can preserve the invariant that s is equals to 0, and the assertion condition is always satisfied. Another example, if f external function f always returns a non-negative value, then we can preserve the invariant that the value of s is always greater than or equal to 0, and assertion safety is true. But these specifications of f are not maximal. Maximal specification of f can be represented by this one. It says that for any argument x, if f of x terminates and returns some value y, then this property holds, this condition holds. This means that if the argument of x is negative, then f can diverge or return any value. It is safe because the open program always pass non-negative argument I to f, so we don't care. If the actual argument of f is greater than or equals to 0, then f needs to diverge or returns non-negative value to satisfy the assertion safety of the program. So we'd like to synthesize such maximal specification from given open programs. There is another work called the refinement type of optimization, which can be regarded as a maximal specification synthesis method for high-order functional programs, which maximize predicates in contravariant type positions and minimize predicates in covariant type positions to obtain maximal specification. These existing work, however, have some limitations such as unsoundness, incompleteness, or the solution of such space is limited to syntactically definable ones expressed by some logic formula. We somehow remedy the limitation and propose a new maximal specification synthesis method. Before explaining our method, let me introduce some notation and terminologies. Our specification of f is in this work represented as a predicate, and we call f specification S is sufficient if the program P is safe whenever the implementation F satisfies the specification. And the goal is to find a maximal specification with respect to this subset ordering among sufficient specifications. And this is our running example. And we can consider these specifications, for example, S1, this represents contradiction, is sufficient, but not maximal. So if that implements the specification needs to always diverge. So it really satisfies that assertion safety, however, is useless. This specification S2 for F says that F always returns, terminates and returns some value Y that is greater than or equal to 0, which is also sufficient but not maximum. And maximal specification we have seen is max is indeed maximal. And this is a unique maximal specification for this example. But in general, there may be more than one maximal specification. We like to find some maximal specification. So our method finds a maximal specification by iteratively improving sufficient ones. And we check if the current specification S is maximal. And if it is not, we construct another refined sufficient specification S prime rather than S and repeat the procedure until a maximal one is found. So in our procedure, in our method, maximality checking is a key component. And our main contribution is a new method for checking maximality of the given specification. Before explaining our maximality checking method, let me first explain sufficiency checking, which can be checked via safety analysis. The idea here is to use an implementation of F that is the worst among those satisfying the given specification S. This is the worst implementation of F that satisfies S. Here, F non-deterministically diverge or returns some random Y that satisfies the specification, which is the worst specification. And then by using this one, combining this with the open program, we obtain a closed program, and we can show that, see that specification, the given specification S is sufficient if and only if P with the implementation is safe, assertion safe. Okay. So sufficiency checking can be reduced to safety analysis, assertion safety. And let me next explain more complex maximality checking, which we reduce to reachability analysis. The idea here is that if the given specification is maximal, if and only if for any external point A, B of S, an extension of S with the external point becomes insufficient. Furthermore, we can say that S is maximal if and only if for any external point of S, P with the worst implementation of F satisfying the S extended with the external point is unsafe. Here, unsafe means assertion violation is reachable. Based on this idea, we can reduce the maximal checking of the given S specification to the unsafety verification of this closed program. Here, this definition of F is the worst implementation of F satisfying specification S. And please note that the external point, the choice of external point is demonic. Here we demonically choose A and B. That is not in S. And for all A and B, we need to prove that assertion violation is reachable. But please also note that in the original program, there are non-deterministic choices, and they can be now replaced by angelic non-deterministic choices. We can choose strategies for angelic non-determinism arbitrarily to prove the assertion violation. Okay. So let me instantiate this closed program by using our concrete maximal specification Smax, which is this one. By replacing S with Smax, we obtain this closed program. Here, we demonically choose A and B that are where A is greater than or equals to 0 and B is always negative. And we can synthesize strategies for angelic non-determinism, blue ones. For example, by instantiating strategies for angelic non-determinism synthesized by our tools, we obtain this closed program like this. And we can now witness reachability to assertion violation by using a ranking function A minus 1 plus 1. That ranking function, the value of that ranking function always decreases when we execute the body of the loop. And this is bounded by 0 from below. So it witnesses that the while loop always terminates. And we can also show that the condition of the assertion is violated because the loop first increments I by 1 by taking the else branch until A becomes equivalent to I. And once A becomes equivalent to I, then we always choose the then branch, invoke the external function f, and please note that f always returns b, which is chosen negative, which is chosen negatively here. So s always decreases by some value, and eventually s becomes non-negative, and loop terminates, and assertion is violated. Yeah, for this example, the witnesses are very complex, but our tool can automatically synthesize these strategy for non-angelic choices and ranking function to prove the maximality of given specification. Okay. Let me next explain. We have used example programs to explain intuition behind our method. And in the paper, we have formalized maximal specification synthesis problems as CHC optimization problems. Maximal specification synthesis problems can be reduced to problems of finding an optimal solution of constraint home clauses by using a standard translation from programs to CHCs and introducing a fresh predicate variable f representing an unknown specification for the external function f to be synthesized. This one can be reduced to this one, which I do not explain in details, but it can be reduced to this one, soundly and completely. And so CHC optimization problem is formally defined either of this form or this form. Maximize x such that C asks to find a solution that is maximal with respect to this order among all solutions of C, minimize X such that S has to find a solution that is minimal with respect to this one among all solutions. Here, X is a set of predicate variables, and C is the finite set of CHCs of either form. I do not explain the definition of CHCs, but yeah, we use a predicate interpretation law to represent a solution. Law is called a semantic solution of C if all the clauses of C are become valid under the interpretation, and the order on the interpretations are defined like this. And it substitutes various predicate constraint optimization problems studied in the literature, CH maximization, match abduction, and so on. I will skip this. And our second contribution is a CHC optimization method based on termination analysis. Sorry. Before that, I will explain a computational theoretical analysis of the optimality checking problem for CHCs. We have shown that every satisfiable CHC has a maximal solution. CHC over the theory of integers has a maximal solution. It is proved by for any theory, it has a maximal solution. It is proved by Zorn's lemma, but I do not explain details of proof. Please see the paper for details. And it is easy to see that every satisfiable CHC has a unique minimum solution. But existence of a maximal solution is non-trivial. We have also shown that the match abduction problem, which is a subclass of CHC optimization over the theory of LIA, may not have a maximal solution expressed as a logic formula in LIA. The same result for LIA has already been shown by a previous work. The theorem has a negative consequence that our procedure of PCSAT that tries to construct LIA formulas representing a maximal minimal solution is doomed to fail in such a pathological case. It's a negative result. We have also shown that the maximality checking problem of CHCs over LIA is pi0 to complete, highly undecidable one, which is as hard as termination analysis of programs. A negative consequence is that an existing reduction of maximality checking to SMT solving is unsound. A positive consequence is that techniques to solve any pi0 to hard problem would be applicable. And we indeed apply termination analysis programs, which is pi0 to complete to maximality. So we have presented PCSAT algorithm, a CHC optimization method based on termination analysis. It iteratively refines the current solution until an optimal one is found, and it performs optimality and non-optimality checking in parallel. And non-optimality and optimality checking are reduced to satisfiability of predicate constraints. Non-maximality checking is reduced to constraint like this that uses non-empty constraint. It says that current solution psi it can be extended by P. Here, the constraint says that psi implies P, and also there is an external point of psi P contains. To express that one, we introduce a non-emptiness constraint, and we can use constraint solver for the new class of constraints to check the non-optimality of non-maximality of the current solution, and we can further obtain a refined solution if the current solution is non-maximal. Okay, we have also presented a constraint-based optimality checker. It is based on the reduction we have already seen. This unsafety verification of this cross program is reduced to a constraint solving problem expressly in POPL'23, and we use these features to encode synthesis of strategy for indirect non-determinism and synthesis of ranking function. I will not explain this in details. Please see the paper for details, and we have implemented and evaluated on our tool using CHC maximization benchmarks. And we obtained promising results. Our tool found optimal solutions for non-trivial CHC optimization problem despite the computational hardness. Okay, and we have also compared our tool with an existing solver. Okay, and that's all. Thank you very much for your attention.
Again, have we got any question from the crowd? We're a bit over time because of the previous questions, so please. Are there... well, let me wait. Was there a raised hand? Then care to use some of the question time, then perhaps to go over the implementation and evaluation details a bit more that you didn't have the time to go through right now. Would you like to go over the implementation and evaluation details?
Okay. How much do I have?
2 minutes.
2 minutes. Okay. We have compared our tool with HornSpec, which is a maximal specification synthesis tool, but it uses unsound SMT-based maximality checker. So direct comparison is not possible. HornSpec actually solved instances more efficiently like this, but our tool, OptPCSat, also found optimal solutions, similar number of instances. And we have also checked whether solutions generated by HornSpec that uses unsound checker is indeed optimal or not, and found that optimal PCSat has successfully shown that 47 solutions out of 57 solutions are indeed optimal, despite the unsoundness of the maximal checker used in HornSpec. However, we found that 2 solutions are non-optimal, incorrectly reported by HornSpec. So our conclusion now is that it is practically useful to combine OptPCSat and HornSpec to complement each other. That's
the speaker again. And,
thank you.